As computing platforms become more complex, with more components generating more data traffic than ever before, the system architecture must optimize data movement throughout the platform to meet performance objectives. Intel Quickpath Architecture is designed to maximize data transfer performance, reliability, and availability in next-generation Intel-based computing platforms. Through current generation platforms, the front side bus was able to keep pace with microprocessor improvements. Tomorrow's advanced platforms feature more cores, more processors, more multi-threaded optimizations, more advanced memory technologies, and more I/O. Intel Quickpath Architecture is optimized for these new platforms, and that means better overall performance for servers and workstations. Intel Quickpath Architecture is both faster and more efficient than previous generation architectures. The throughput between components is faster than before, and it features high-speed point-to-point interconnects between processors in the platform. There are dedicated paths in each direction between components so that data can simultaneously flow both ways. The architecture also supports a high degree of parallelism, meaning data can move at high speeds across any or all connections simultaneously. Intel Quickpath Architecture also moves data more efficiently. For example, there's an optimized method to manage and share cached data between processors. Let's compare how it works versus other architectures. Imagine Processor 1 needs data located in Processor 4's memory. Some architectures would request the data from Processor 4, which would then ask the remaining processors if they have a more recent instance of that data in their cache. The remaining processors would respond, and only then could Processor 4 deliver the data to Processor 1, requiring 4 hops to complete the transaction. In contrast, the Intel Quickpath Interconnect Snoop strategy starts by sending simultaneous requests to all processors. The processors then respond to Processor 4, which owns the memory where the data resides. Processor 4 then delivers the data to Processor 1, completing the same multi-processor transaction in just 3 hops. Additionally, the Intel Quickpath Interconnect uses an efficient cache-to-cache data forwarding technique. Assume Processor 1 needs data in Processor 4's memory. Under certain conditions, if Processor 3 has a local copy of the data, it can immediately return it to Processor 1 in response to the snoop it received, delivering data in just 2 hops. Processor 4 still verifies there are no conflicts, informing Processor 1 the data it received is current. Payload efficiency is another performance enhancement. This speeds data packet transfers by requiring fewer clocks to send header and CRC information compared to other architectures. Intel Quickpath Architecture also transfers CRC error detection data in parallel to the packet itself, whereas other architectures transfer CRC data sequentially after the packet's payload. And Intel Quickpath Architecture includes 72 CRC bits versus 32 CRC bits, so transfers aren't just faster, they're more reliable. Intel has designed a holistic platform solution to speed data movement to applications regardless of the data's location. Preferably, requested data would be in the cache of the processor that's running the application, which is why Intel's next-generation microarchitecture, codenamed Nehalem, features a large, intelligent cache design to minimize latency. The data may also be located in another processor's cache, which is why the Intel Quickpath interconnects were designed to deliver high-bandwidth, inter-processor transfers. But regardless of other efficiencies, data must sometimes be accessed from system memory. There's a low-latency integrated memory controller tightly linked with each processor. Each controller in the initial launch of the system architecture includes 3 data paths to system memory rather than 2, and the paths are up to twice the frequency of common DDR2 667 memory, multiplying total bandwidth by up to 3x over today's platforms. When combined with Intel's other latency-reducing, performance-enhancing features, the integrated memory controller further accelerates data access speeds. The rapid movement toward virtualization and application consolidation makes reliability, availability, and serviceability, or RAS features, more important. The Intel Quickpath architecture has many innovative RAS features integrated throughout its subsystems. For example, a RAS feature built into the Intel Quickpath interconnects sends 72 CRC bits per packet for increased reliability versus competitive architectures that send less than half that total. And those CRC bits are sent in line with the data, which improves performance by reducing the total number of cycles required to transfer the data and CRC bits. It also enables self-healing capabilities in expandable servers that have the most stringent availability requirements. There are 20 lanes grouped into 4 quadrants, and the link is able to send data in full, half, and quarter width modes. Transfers are retried until successful to prevent data loss. When a persistent error is detected by the receiver, the data is automatically retried, with the system adjusting quadrant usage to avoid the problem lanes. Lanes in the other direction are not affected. The system also intelligently logs errors. There is also a clock failover mechanism. If the clock fails, a similar process adjusts the link to half or quarter width mode, and the clock is transmitted over a predetermined data lane. These are just a few of the RAS features built into the Intel Quickpath architecture.